Welcome everyone. Today we'll solve some problems about sets and we will finish our class. So let A, B, C be any sets, show that equations are correct. Okay, so we have a couple of equations that we need to show that these are right. So if we remember that if A is a subset of B and B is a subset of A, this means this is only possible when A is equal to B, right? So if we want to show an equation is correct, we will start here and we will finish here. And then we will start here and we will finish here. But don't worry, after doing the first part, doing the second part is way easier because it's just being directly backwards. So let's begin. X belongs to A minus A. This means X belongs to A and X does not belong to A, right? This also means that X belongs to A and X belongs to A complement, which means X belongs to A intersection A complement, which is an empty set. So we started here, we finished here. If you write this the same way, just backwards this time, what I mean by this is if X belongs to empty set, that means X belongs to A intersection A complement, and this means X belongs to A and X belongs to A complement, and this also going to mean that X belongs to A and X does not belong to A. This is going to give us X belongs to A minus A. So from these, we can say that A minus A is empty set. What did we do? We started from here, we finished here, and then doing the same thing backwards, we started here, we finished here. This means that we showed that this equation is correct. We will always do the same thing. It's not a hard thing. So we're gonna start here from the left. Let's start. X belongs to A intersection B. This means X belongs to A and X belongs to B. This means X belongs to B and X belongs to A. We can do this, right? Yep. Therefore, X belongs to B intersection A. We started A intersection B, we started B intersection A. So this is correct. Let's do the same thing backwards. We're just gonna write it we can just start here and finish here. It's the same thing. B intersection A. This means X belongs to B and X belongs to A. From this we will get X belongs to A and X belongs to B. This is going to give us X belongs to A intersection B. From these, we can say A intersection B is equal to B intersection A. We can do the same thing for union. X belongs to A union B. So X belongs to A or X belongs to B. Be careful. For union, as we said in the last video, we use OR. For intersection, we use AND. X belongs to A or X belongs to B. Therefore, we can say X belongs to B or X belongs to A. It's the same thing. So this means X belongs to B union A. Why did we start? Why did we finish? I will leave the backwards to you guys. It's just writing the same thing backwards. Let's move to the last example for this part. Okay, this is... Wait, is this correct? A minus B. Yeah, it is correct. So we will start here. X belongs to A minus B intersection C. This will mean that X belongs to A. We must be careful here so we don't do a mistake. And okay, X does not belong to B intersection C. Well, we could say X does not belong to B or C, but I'm gonna do something, a little trick here, so I wrote it like this. This means x belongs to A, and x belongs to complement of B intersection C. Because if x does not belong to A, it belongs to complement of A. X belongs to A and x belongs to B intersection C. Complement. Okay, so from here we get x belongs to A and x belongs to, if we use the De Morgan rule, B complement union C complement, right? So we can say, and x belongs to B complement, or x belongs to C complement. And this means x belongs to A and x does not belong to B. Wait, x belongs to A and x belongs to B. X does not belong to B, or C. What we want to show is, yeah, okay, so now what we're gonna do is, we will say that x belongs to A and x belongs to B complement, or x belongs to A and x belongs to C complement. So what did we do? We just did it how we do it in math. So you can do it in with do it with sets as well. It's not always, it will work fine. Therefore we get, for x belongs A and x belongs B complement, we get x belongs A intersection B complement, or x belongs to A and intersection C complement. This is going to mean that x belongs to A minus B union for R or and A minus C, because as we know, A intersection B complement is A minus B. We saw these yesterday. Showing it backwards is, I'm leaving that part for you. Show that for every set of B, B complement of B and the B complement and complement of it is equal to the original set we have. So how do we show it is, of course we're going to take an element from B, B complement, so B complement, and this means x does not belong to B complement, because if x belongs to A complement, if x does not belong to A complement, for example, it belongs to A, right? So the same idea works here. It's just we have another complement. So x does not belong to B complement, but this means x belongs to B. So therefore, we can show it backwards the same way. X belongs to B. This means x does not belong to B complement, and this means x belongs to B complement. So from here, we can say E complement, and the complement of it equals to B. Okay. Is this our last question? Yep. Figure out the answers in 6-9. Okay, so we have a symmetrical difference. We talked about it yesterday. I told you guys to remember it, but still we're going to give the formula here. Asymmetrical difference B equals to A minus B union B minus A, right? So we will just use the formula to solve these. We have one formula for symmetrical difference, we'll just use it. So what we have here is B minus, okay, the ink to shape it as usual, right? B minus B union B minus B. So this means, what does B minus B means? Of course, it's an empty set. Empty set union empty set is gonna give us another empty set. Therefore, this is empty. This is an empty set. So we have asymmetrical difference empty set. Okay, so this means A minus metrical empty set union empty set minus A. So this will give us A union empty set. Here, this is A, and this will give us A, and this will give us empty set. And so here we get A. Okay. Why did we write this? Oh, we need to show that asymmetrical difference B is equal to B symmetrical difference. Okay. Let's do the 9 first, and let's do the 8 later. So, okay, we have A minus A complement union A union minus A. So, what we know is, from here, we're going to get A. And from here, we're going to get A union, A complement. Sorry. So, we talked about this in this video. A union A complement is going to give us the universal set. So this is U. Okay, now let's move on to the 8th and the last question. A symmetrical difference B equals to B symmetrical difference A. We need to show that this one is true. Okay. A minus B union B minus A. And for this, we get B, not beta, B minus A. I keep calling it beta today. Union A minus B, right? We know that in unions, we show that A union B is equals to B union A. We know this is correct. So we can say the same thing here. We can change these. It's completely fine. So therefore, our 8th equation is also going to be correct. These are all examples that I want to solve for its sets. Thanks for listening to me this far. Have a great day.